Yesterday, we started doing calculations, and we did the last calculation of a weak acid being titrated with a strong base. Here is the secondary question that goes along with that. So, in this case, we are being presented with the fact that we have to calculate the pH at the equivalence point when we've added 40 milliliters of 0.25 molar benzoic acid. Now, there's a couple things that we need to consider here. First of all, benzoic acid is definitely a weak acid. Benzoic acid is definitely a weak acid, and sodium hydroxide is definitely a strong base. We should probably consider a little bit of what's actually going on in terms of the reaction. So first of all, I'm going to say that we have benzoic acid, which I'm just going to call H. Well, I'll do it this way. H-ben for the benzoic acid plus the NaOH will react to form essentially water and Na-benzoate, which is C6H5COO. Now, the issue with that is that we don't know how much of the acid is, or the base has been added, so we have to do some calculating to kind of figure that out. We also know that we are at the equivalence point, and the equivalence point tells us what is equal to what? At the equivalence point, what is equal to what?
Concentrations, or is it the?
Not the concentrations.
The moles?
The moles of acid is equal to the moles of base, okay? So in this particular problem, one of the things that we have to figure out is we have to figure out essentially how much sodium hydroxide has been added at some point, but we'll get there. Now, the first thing we need to figure out is how many moles of base are actually there. And so here's how I'm going to go ahead and calculate that through. So if I know the concentration of my weak acid, and I know how much of the weak acid I have, I can figure out the moles of weak acid present. So what I'm going to do is I'm going to take molarity is equal to moles over liters. So we know the molarity is 0.025 molar will be equal to moles over the, in this case, 0.0400 liters. So that will give me 0.001 moles of the benzoic acid. Okay. And if we are at the equivalence point, what does that tell us about the amount of base? It should be the same. So that would tell me that I would have 0.001 moles of NaOH at the equivalence point. Now remember, with this type of curve, weak acid, strong base, our equivalence point is above a pH of 7. So we have to keep that in mind as we're going ahead and doing this. Now, the other thing that we have to figure out here is that when you are adding a strong acid to a weak, or I'm sorry, a strong base to a weak acid, we end up creating a buffer on accident. So, well, not on accident, but it really happens. So like what I'm going to do is I'm going to erase this guy right here, and I'm going to kind of get to my buffer here. So in this case, I have my benzoic acid, C6H5COOH, plus water will react to form C6H5COO minus, and eventually the OH minus. So that's our buffer system that's being created when we add sodium hydroxide. Does that make sense? So here's our neutralization reaction, and here's our buffer that's occurring as part of that. Now, the thing is that now that we know the buffer system, in order for us to calculate the pH, we have to figure out the concentration of the base here. So we know the concentration of the benzoic acid, but we really need to figure out the concentration of the conjugate base. So what I'm going to do is I'm going to flip that buffer system for a second. So I'm going to rewrite the buffer system to be Just want dark green. Why can't I have dark? I don't know. Okay, so I'm going to rewrite the buffer system to go this way. And that is going to give me the ability to now go ahead and figure out the KB and the KA and eventually the pH. Thank you. So the next thing that we need to do is we want to figure out the moles or the molarity of the benzoate ion. And what I'm going to do in order to get the molarity of the benzoate ion is I'm going to figure, I know that that's the amount of benzoate that's present. So if this is the moles of the base, the sodium hydroxide, that's also at some point going to give me the concentration of the weak base as well. So what I'm going to do is I'm going to use that, and I'm going to divide it by the total volume in this case, which would be 0.040 liters plus 0.050 liters, which will give me 0.0167 molar. And what this really is that's the concentration of the C6H5COO minus. Yes?
When you flipped the equation, why didn't you also move the OH to the same side as the...
Because in this case, if I move the OH over there, nothing would happen. So I'm hydrolyzing the base at this point.
Okay.
Yes, sir.
Oh, wait, where'd you get the 0.05 liters that you added?
Where did I get it from? Oh, it should have been 0.05. I miswrote. Hang on. It should have been 0.02, which is still the same question you're going to have.
Yeah.
Okay. So the other thing that, in order for us to get to that particular point, what I did was I used moles of acid. Sorry, I skipped this step. Volume of acid equals moles of base, volume of base. So I use the 0.025 molar my acid and my 0.040 liters equals the concentration of the base that was added, which was 0.020 liters times volume of the base, which moved over to become 0.020 liters, which...
Oh, you put 0.02 as the molarity for MP.
Oh, that should be 5. Look at you, catching all my mistakes today. So that's where I got that from. So now that I know the concentration of my benzoate ion, I can set up my ice table. And now that I've set up my ice table, what I need to do is realize that because this is my conjugate base, even though I was given my Ka, I have to determine the Kb before I can go much further. So in order to determine my Kb, I need to remember that Ka times Kb equals Kw. So the Ka was 6.3 times 10 to the minus 5 times the Kb, which is what we need, equals 1.0 times 10 to the minus 14. Kb in this case will end up being equal to 1.6 times 10 to the minus 10. Yes?
Should we always just assume that it's at room temp? No.
Yes. Yeah.
What does that number say?
1.6. Yeah, always assume it's at room temperature. for these types of problems. The College Board, I don't think is gonna get any crazier about like you need to adjust temperature and things like that. Okay,
If they give us a KA and a KW that's different from the one that we memorized, then we would have to assume that it was a different temperature, right?
correct. So if they gave you a different KW, like, remember how, you know how like when I give you test questions and they're like, step 1, do this, and step 2, do that, and step 3, do this, and a lot of times they kind of all flow together? I believe that the College Board, if they wanted you to work at a different temperature, they would give you a KW of something else and have you calculate like the KA at that temperature based on how we did in the last unit. And then from that point forward, you'd use all of your values off of that. But I don't think they'd be like, whoa, hold on a second here. By the way, you have to do all this work in this problem and then change it to a different temperature. I think they'd start out with that as a simple 1-point problem to begin with. So that's our KB. So now I'm going to write my KB expression, which would be concentration of C6H5COOH over OH minus, or times OH minus, over the benzoate ion. I know my KB is 1.6 times 10 to the minus 5. Top is going to be X times X over 0.167 minus X. Which will get me a value for X to eventually equal 1.63 times 10 to the minus 6, which will equal my X. From there, I can
0.67 or 0.0167?
point 0.0167.
And we still do that thing where we
Assume that X is negligible, yeah. And I would say that if I had 1.63 times 10 to the minus 6 divided by 0.0167 times 100, it's like 9 thousandths of a percent. So I think we're good. So now I can go ahead and calculate my POH.
Did the answer change at all when you added in the extra 0?
No.
Okay.
No, I just mistranscribed from up here. So the POH here will be 5.76, which would get me to a pH of 8.21. So this is at the equivalence point, and because this is a weak acid being titrated with a strong base, the equivalence point has to be greater than 7.
Wait, say that again?
Because this is a weak acid being titrated with a strong base, the equivalence point has to be greater than 7. Maria,
Backing up a little bit, it says for the original KB that it's 1.6 times 10 to the negative 10. And then if you go down to where you're solving for the concentration, actually solving for the KB, it says that it's 1.6 times 10 to the negative 5.
Oh, yeah.
appears I transcribed wrong. Appears I stink at writing today. Or in general. Why are you not erasing? Well, that's fun. Why is it not erasing?
Technical issues?
Appears that way. All right, then we're just going to change that to 1.6 times 10 to the minus 10. Sorry, my bad. Moving on. Question.
Why 8.21?
14 minus 5.76.
Let's do 4.
2-4, yeah.
Well, again, apparently I transcribed, there should be 9. Seriously, it's 9. Right? I just can't
We
write.
only have one more day left this.
Of course.
Are we just ignoring the majority species or?
What would it be? Sorry. No, seriously, what would it be?
C6H5COO minus.
Well, in this case, yes, our pH is incredibly basic, so it's got to be it has to be the base. And in this case, yeah, it would be the C6H5COO minus. Can I move on now? I know.
It's good. Enough for.
Yes?
Can you just go back for a second?
New idea. Strong acid titrating a weak base. Oh, man. So take a look at that curve. That's a beautiful curve. Note that we are starting with a pH greater than 7. We run through a buffer region. We eventually reach the equivalence point, which is a less than 7, a pH less than 7, and then we get incredibly acidic. So, a couple of things to keep in mind. The midpoint of the buffer region is known as the half equivalence point. It's known as the half equivalence point, in which case the pH would be equal to the pKa, because remember the concentration of the base is equal to the concentration of the acid at the half equivalence point. The concentration of the base is equal to the concentration of the conjugate acid. Any questions about that? Moving on. What volume of hydrochloric acid is needed to completely neutralize the base?
40.
I would say 40 milliliters. What volume of HCl is needed to reach the half equivalence point?
20 milliliters.
20 milliliters. What's the majority species at the half equivalence point? Right, they'll be the same, yeah. What's the majority species before the half equivalence point? The base in this case? NH3. What's the majority species between the half equivalence point and the equivalence point?
HCl.
Well, we're going to say acid because it's probably some combination of the NH4 plus and the HCl. And then what's the majority species at the equivalence point? The acid. Questions about that? So far, so good? Or bad? Or whatever?
That's not very optimistic.
Have you seen my writing today? My ability to transcribe today? All right. So here's a plan to think about. If it's strong acid, weak base titration, before titrating, you only have base present. So there's nothing other than base. So we can use an equilibrium calculation to calculate the pH. Once any base has been added, but before the equivalence point, you both have base and some conjugate of the base, and we need to use buffer chemistry to get there. At the equivalence point, all of the base is gone, and the solution is all HB plus, or conjugate base, which undergoes hydrolysis, and you have to calculate the new concentration of the conjugate base. You have to find the Ka from the Kb of the buffer region, and then you can calculate the H plus to eventually solve for the pH. Anything past the equivalence point, you just calculate the new volume of the H2O plus and calculate the new pH. Questions about that? We're going to work through a couple things. Are added. So this is before titrating. There's only base like this. I'm going to just apologize for the amount of room present. So sorry. It's not a lot.
Oh,
I don't know.
Big.
We have an entire, like, page and a half
No,
that we could have extended our notes to.
what?
I think we got a lot of margin
bring up
space.
good points.
There's-
I'm bringing up good points, why would you stop me then?
Because she thought you were going somewhere else.
Yes.
She thought you were saying, we'll do it on the other side.
Oh.
Anywho. In this problem, you said that you have 90 milliliters of 0.6 molar ammonia. You're told the KB, and you have 1 molar hydrochloric acid. That's pretty much all you're told. Yes, ma'am?
No.
Oh, big stretch. Big stretch. Okay. It's like a big kitty stretch. All right, now. You don't have cats, huh?
I have 3 cats. I know what you're talking about.
And they all
I
do
just
that
never
weird
thought
big
about that.
stretch.
My
Yeah.
dog does that. She also looks like a cat, so.
What kind of dog do you have?
Big Pomeranian.
Oh,
Fair.
that explains it.
I have a cat that acts like a dog. Yeah, greets me at the door every day.
I have a cat
No,
that acts.
that one's lazy as crap. All right, now. So in this case here, it says, what is the pH of a solution before any acid is present? So we are going to use an ice table. So what I'm getting at here is that in order for us to calculate the pH, this one's not too hard because we've already done stuff like this before. You just have a beaker of 0.6 molar NH3. So the reaction that I'm going to write is NH3 plus water will react to form NH4 plus and OH minus. And I'm going to make this an ice table. And I'm going to start with my 0.60 molar, not worrying about the water, 0 NH4, 0 OH minus. Going to subtract X, add X, and take 0.60 minus X, and the X. And because this is a base, right, I'm going to write my KB expression. So KB is going to be equal to NH4 plus OH minus over NH3, like that. So I know my KB value is 1.8 times 10 to the minus 5. I know NH4 is X, OH minus is X, and I'm left with 0.60 minus X here. We are going to assume that the X is incredibly tiny, and as a result of making the assumption that the X is incredibly tiny, we're just going to go ahead and solve. So when all is said and done, I get a value for X that is equal to 0.00327 is equal to X, which is also equal to OH minus. So if that's equal to OH minus, so if that's equal to OH minus, I now can go ahead and calculate my POH. So POH is equal to negative log the OH minus. POH is equal to the negative log 0.00327. The POH is equal to 2.48. And the pH then would be equal to 11.52. And even I can do the math in my head to know that that one adds up okay. It's been a rough day.
That was enough room.
What?
I fit it in.
Yeah,
Yeah,
but wait,
He's talking
just
about
wait
being
until the next one, it'll probably take up way too
No,
much
I did
space.
better writing this time.
This time. Did you
Well, last
mess up
hour,
last
no,
time?
it wasn't so much, you know, I mean, they're gonna complain, I didn't write very well last time, but like, it was more or less organized. Okay, now, B, hi, how's it going? It says, what is the volume of acid needed to neutralize half of the NH3. Well, let's see if this works out. So in this case here, we're saying half of the NH3, right? So what that tells me is that if I take 90 divided by 2, that's how much?
45.
That's 45, right? There is a part D.
Oh my goodness.
Sorry.
I know, it's gross. Okay? So we're gonna see how this works out. So if I take, so if we're neutralizing, what does that mean?
It's that they're equal concentrations.
What's equal, not concentrations?
The mole.
Moles of acid is equal to moles of base, right?
Okay.
Okay? So in this case, if I know that my new volume is 90 divided by 2, which is 45 milliliters, right? So if I want to neutralize half of that, molarity is equal to moles divided by liters. Molarity, nope, not molarity, that's silly. 0.60 molar NH3 will be equal to moles over 0.0450 liters will be equal to 0.027 moles of NH3, which should be equal to, so that's my moles of base, right? So that should be equal to moles of acid. Okay, which in this case is HCl. So that should be equal to 0.027 moles of HCl. Now, in that case, we still need to figure out the volume, so that's moles. So what we're going to do is we know the concentration of the HCl was 1.0 molar is equal to the 0.027 moles, and we need to figure out the volume if molarity is equal to moles per liter, right? So when I move over and I do the math associated with that, I get 0.027 liters. Right? So that's the amount of acid needed to neutralize half of the NH3.
Is that the half equivalence?
Yeah. Good call. This would be the half equivalence point. Oh, looks like I made a fish.
So does the house equivalence point always have to be half of what, like, whatever's being titrated then?
Many times. I mean, it's always, like 99% of the time, yeah. So how's that feel? Moving on? This might be the one where things got a little hairy. No, it's not too bad. All right, so in this case, it's asked to calculate the pH after 50 milliliters of acid has been added. Okay, so we have our NH3, so I'm going to write this at the top. NH3 plus HCl will react to form NH4 plus and Cl minus. Okay. Now, in this case, the chlorine is our spectator ion, so it's kind of a moot point. But in reality, we again have our buffer system that we have to kind of keep track of. So the question is what is the pH after 50 milliliters has been added? So we know, so now at this point, we're gonna kind of forget about the other thing, so I'm gonna go back to, I'm gonna write this a little nicer. So if this was 0.60 molar, and this is 1.00 molar, right? Okay. What I'm going to do now is I'm going to change the color, and I'm going to identify the number of moles present. We decided that this was 0.054, right? No, we didn't talk about that, but we'll talk about that in a second. So molarity is equal to moles per liter. If we have 0.60 molar equals moles over 90, geez. Over 0.090 liters, that gives me 0.054 moles of the NH3, right? And in this problem, we knew essentially that the amount of acid that we were using was 50 milliliters. So I'm going to do that calculation over here. So I'm going to take the molarity is equal to moles per liter. So that was 1.00 molar is equal to moles over the 0.050 liters, which gets me to 0.050 moles of the HCl. So far, so good with that. Yes, no? So now, in this problem, if we're going to look at it from the perspective of what was left over and what all happened, what I'm going to do is I'm going to cancel that out for a second, and I'm going to replace it with the 0.050 moles, okay, and the 0.054 moles. So what's my limiting reactant going to be here? Good. So I'm going to subtract and so in this case here, I have 0.004 moles left over and 0.050 moles produced. Okay, and I'm ignoring that. Now, what have we created here? We created a buffer because we have some base, and we have some conjugate acid. So I'm going to now rewrite this as a buffer system. So I'm going to take the NH3, I'm going to hydrolyze it because all the hydrochloric acid is gone. I'm going to produce my NH4 plus and the OH minus. Now, are you okay if I skip to the after line here? Yeah?
Like after the OH2.
Like in order, these two values here are essentially my after, but to get there, I had to show you that the hydrochloric acid wasn't present, right? So in reality, I really had 0.004 moles and 0.050 moles and 0.050 moles. Now, the next thing that we need to do is calculate the concentration of the new concentration of the NH3.
Wait, where did you get the OH minus or moles?
Because in this buffer system that we created here is here, right? You see that? But like this amount that was left over still hydrolyzes, but it hydrolyzes with what was here at the end. And as a result of that, we're going to make that amount of water, or hydroxide as well. But it kind of doesn't matter because we're only calculating the NH3 and the NH4 at this point, because we're going to use Henderson-Hasselbalch. So in this case, I'm going to take the concentration of the NH3, which is 0.004 moles, divided by the total volume, which in this case was the so that gives me the concentration of the NH3. In order for me to get the concentration of the NH4, I'm going to take the 0.050 moles divided by the 0.090 liters plus 0.050 liters, because that's how much the solution is now. And that's going to give me a concentration of 0.357. So now I'm going to use Henderson-Hasselbalch equation. And when you're using the Henderson-Hasselbalch equation on the base side, it's conjugate acid divided by base, whereas on the acid side, it's the reverse. So in this case, I have the POH is equal to the PKB, which I need to calculate. But I can calculate because I know the KB from the page before. So I'm going to do that over here. PKB is equal to the negative log of the KB. So the PKB is equal to the negative log of the 1.8 times 10 to the minus 5. So the PKB is equal to 4.74. So my 4.74 is here. So when all is said and done, I get a POH equal to 5.84 and a pH equal to 8.16.
Would you say that's the most difficult thing we'll have to do with this?
It's a lot.
So would you say that it's the most difficult thing that we have to do with this unit?
Complicated multi-step thing, maybe?
Yeah.
Yeah.
Okay.
All right, now, last thing we have to do is identify the pH at the equivalence point. So, we know a couple of things. One of the things that we know for sure is we know that the concentration of the NH4 plus is equal to 0.357 molar, because we just calculated that above. And so we also know that if we take NH4 plus and hydrolysize that, we get NH3 and H3O plus. So if I take an ice table and I take the 0.357 molar minus X plus X plus X, I get 0.357 molar minus X, X, X. I can then write a Ka expression because we are trying to calculate the pH at the equivalence point. And if you remember, in this particular case, because we've added so much acid, we are now acidic, which is why I wrote the ice table for the conjugate acid here. So my Ka expression is going to be concentration of NH3. Oh, geez, words, letters are hard. And the H3O plus over the NH4 plus. And so, room, sad. Okay, so at this point, I'm going to go ahead and calculate my Ka, because I have not done that yet, so I'm gonna do that over here. So Ka times Kb equals Kw. Ka times the 1.8 times 10 to the minus 5 equals 1.0 times 10 to the minus 14. Ka will equal a value of 5.6 times 10 to the minus 10. So let's plug in some values. So I'm going to take the 5.6 times 10 to the minus 10 equals X 0.357 minus X. And I'm going to get a value for X in this case to be equal to 1.44 times 10 to the minus 5. So from there, I can now calculate the pH, which is the negative log of the H3O plus. The pH is equal to the negative log of the 1.44 times 10 to the minus 5. The pH is equal to 4.84, which is approximately where we should end because, or at least the pH should be, because we added a lot of acid to a weak base. Now, well, as much as I would like to go on and take a look at example number 13, a lot of them are just things like that, labeling and answering questions. Do you see this? Do you see this giant thing right here? I'd start those tonight. Just telling you. Definitely start those tonight.
But it's not due?
Tomorrow, no.
So
Because
it's due after spring break?
Why do we have to definitely start?
there's a lot of them.
Just to make sure that we
Don't we
understand
definitely
it.
have